So during the development of DROPSTAR, we had three challenges actually. One of them was to function and perform nominally on all of the components inside the rocket. We also had to make all these components work at the same time without affecting one another. And we also had the functionality that we had to communicate with the ground station and have a functional ground station showing all the data that the person who's on the ground station needs to see. So one of the biggest challenges to me was the communication with the rocket and making the components work in parallel, basically.
BEAM stands for Beyond Earth Aristotle Missions, and it's a student group based in the Aristotle University of Thessaloniki that takes up innovative projects in the space sector. The team was created in 2018, and since then we have 6 projects, mainly projects that participate in the Rexus-Bexus program.
By designing the electrical components of the DROPSTAR electronics, I have gained many insight, mainly how to transform a circuit from designing into a real-life actual system.
Very memorable and exciting moment was when we passed the EAR, which is the Experiment Acceptance Review. So we had some difficulties in manufacturing the device, and it was the first time that we demonstrated the whole system of the device, and it was accepted in order to proceed to the launch campaign.
One of the biggest challenges we had during the initial designing process was the testing of many of our components. That was because many of those were SMD, meaning that they were only soldered onto a PCB and they couldn't be put on a breadboard. So that delayed quite a lot the whole testing process, and what we ended up doing was getting some simpler components, testing those on a breadboard, and then moving on to the actual components we needed.
The part that I enjoyed the most during the promotion of DROPSTAR to the public and the stakeholders is the reactions that we receive. It is very exciting to see that everyone, when they hear about DROPSTAR, they want to know more about the experiment and our work. And I'm especially happy when we are promoting the experiment to students, because you can see that they get motivated to maybe be part of such a project in the future. And this was one of the goals of our team, to open up a new path for students to explore in the future.
My experience in BEAM has influenced my academic aspirations and my career by completely derailing it, I would say, because I thought I wanted to do one thing and it turned out I want to do a completely different thing. The good thing about these projects is that you come in contact with so many sectors, so many things to do, and since you are a student, you have the option to take part in whatever piece of the project you want to. So I found myself doing science, mechanical, and a bit of electrical, and I decided that I actually like engineering very, very much, and my prospect is now to become a space engineer. So in order to talk about the applications and the implications of DROPSTAR science, we first have to state what DROPSTAR is. So generally, DROPSTAR is a study of the stability of emulsions in microgravity conditions. And initially that may sound very, very specific, although there are applications or possible applications for emulsions in microgravity conditions. For example, transport of fuel in space in the form of emulsions. DROPSTAR is not limited to that. Our results and our data can be interpreted as a general stability of emulsion study. And because of that, it can possibly be used by the multitude of industries that use emulsions, such as the oil industry or pharmaceutical industry, and whoever just uses emulsions and is interested in their stability.
So I was mentoring, let's say, the BEAM team during the execution of their experiment. Since I'm working also on emulsion stability, I provided the team with all my knowledge regarding emulsions. Since I have studied with different techniques emulsion stability, I tried to provide them with all the necessary information and details regarding the techniques and the emulsification process. Working with the BIM team was a great pleasure. It is remarkable that undergraduate students from different fields have both the courage and the passion to work with such difficult and demanding projects. I hope that many other students and new scientists will be motivated from this team.
DROPSTAR is the first Greek experiment that was executed in a Rexus rocket. It's BIM's third participation in the Rexus Bexus program, and the Rexus Bexus program is a program that is organized by the Swedish and German Space Agency in collaboration with ESA, CHARM, SSC and Eurolaunch.
So there are many ways to make a system more robust, not only for space applications but for general applications as well. The first way is simply to make it redundant. In our case, we only had one shot to make the experiment work because we only have one rocket flight. So redundancy is very important. So in the case, if something goes wrong, you have something instead of nothing. Maybe not the whole picture, but you don't lose the entirety of your functionality. The second part is simply to make your system robust in ways that don't cost you. For example, we assumed and we were told that we can receive up to 32 volts from the experiment service module, which is our power supply for the experiment. So we could just go for 32 volt capacitors, but there's simply no reason to do that when 50 volt or 100 volt capacitors cost virtually the same and are almost the same size. So you basically step up to predict unforeseen circumstances. For resistors, you don't have to use 04, 02 size resistors. You can use bigger resistors and also have the opportunity to switch them yourself if something goes wrong. So just make your system more robust in ways that don't harm you. As far as testing goes, because that was part of the design, thermal, vibration, functionality, and vacuum testing is necessary in order to catch problems early on. If you pull a vacuum and you see that one of your systems simply doesn't work as it should, then you know you have to redesign or have to reconsider the way that it functions. And we do all these tests to make sure that what goes wrong doesn't go wrong during the flight. Finally, we run several timelines, just our experiment and also integrated with the rest of the rocket. So we run a countdown with all the experiments running at the same time to also catch any interferences between the experiments and make sure that we catch them before we are actually in space.
That would be when the necessary funds for constructing the experiment and the other needs of the team were secured. And that's because DROPSTAR was the first Greek experiment on a Rexus rocket, so it required a higher budget than any other project that previously happened in BIM. And it was one of my top priorities to make sure that the need of every sub-team was covered. And when that happened, I was very relieved and very happy.
It has contributed a lot because I gained experience working as a team member. I gained new insights in space industry. I had the most valuable experiences of my life, I could say. So far, especially on the launch campaign, it was a very exciting period of my life there, and I did gain great experiences, and I wouldn't change it for anything else.
The most rewarding aspect of being a team leader in Project DROPSTAR has been to see all of the work come together and have a successful experiment. When we were selected in the Rexus Bexus program back in December 2021, we naturally focused on the work that was ahead of us, and now that the program is concluded and we had the launch of the rocket in March, we can take a step back and see what we have really achieved. And saying that you are the first Greek team to have an experiment on a Rexus rocket, it sounds grand and you're very proud.